You have started already? Okay.
Yeah.
So the recent one is my research is about the time reversibility. I mean, that's one of the big things, right? The charge parity and time reversibility is the big thing, and the time reversibility is a big thing because I found I'm going to show you after this. I saw a paper that people have done some experiments to show there may be a small time reversibility, which probably will almost as an evidence or proof of what I have done already published. Uh, People never thought it's possible because grandfather paradox, things like that, have been proven to be wrong. So we know macroscopically time is irreversible, but so that's what this one talks about. Uh, uh, Macroscopic irreversible time, but the microscopically, which I didn't put explicitly here, is reversible. So this paper covers that. You can see this paper. I talked briefly about that in the uh, Physical Science and Biophysics Journal of this month, of the last month, but published this month. So essentially, it's a unified framework. So this continues with my previous work, which I showed and discussed with Christopher, and even Emmanuel was there. So we are very deep uh, aspects about early universe, which I said is starting from a superluminal condensate, which was presented in the TEDx May Global Conference in Budapest. Uh, so it is a continuation of that. We believe, and Emmanuel and I started that, the power condensate, superluminal condensate, that realistically, what I have shown is that it doesn't really violate uh, general relativity in any way. Uh, it's with confirming that. And also, I showed that that is very cogmare uh, that can fluctuate randomly, and there is a agent called monopoles, which makes provides that energy, and GAN unified theories have proved that realistically you can you should have monopoles, but it does violate Gauss theorem. So that was the big problem, per Maxwell equations. So how to get around that is that, yeah, the early universe, it could have violated Gauss theorem, and these monopoles could exist and they could be randomly going around. But at some point they come together, and I have shown that, and they produce a locking mechanism where it creates a dipole, which we call it Horde, with the talked with the John Hodge and a few of our researchers, including Christopher Emmanuel and Ben Zong. So we all put together that and said that there is definitely possibility that this could happen. So we have some few papers which talks about that, but the last one, the early universe, which I showed, um, like you know, uh, 2 or 3, the beginning of this year, the New Year presentation. Uh, so I'm not going to go into that. Essentially, it showed that there could be a massless bending because of the magnetic aspects. It's called the Melvin universe, and I showed that it can bend. And as we know, that's one of the key aspects of general relativity, that the space-time local bending is what causes gravity. So once you have the gravity well, so to say, it can creates a crucible or uh, place where you can have particle generation. So now the supernova things, is the speed is reduced by the gravity, and almost like a micro black hole formations can occur, and everything is reduced and the particles can form and hadrons can form. So mainly we know that one of the most stable particles ever since supposedly the Big Bang is the baryonic matter, which is essentially based off protons. The protons, and we know that the protons form isotopic hydrogen. That is the fuel for all galaxies, stars, and everything. So that's the most common, material. Uh, so you describe hot PDP mechanism by it shows a circuit that creates the positron electron north and south monopoles together. They create the mechanism. Uh, it is early to Higgs mechanism. It's more fundamental thing that Higgs mechanism that to create particles per se from the fields. So now we have fields and particles. Uh, so essentially, that's what the main aspect of the previous early universe. This is what I describe here. So explore particle formation, building the recent paper on early universe magnetogravitational genesis mechanism. So then this paper talks about how it gets stabilized, how the hadrons get stabilized. And that's the main thing. So it forms like a quantum lattice, and we can it's shown by discrete Lagrangian and quantum cellular automata, which is very well known in the literature. And using the literature, people have explored this aspect. So, so essentially, what happens is earlier I described the time is actually not just scalar, but it could be a tensor, a rank six tensor. And the future is where all these are possibilities and then collapses because of the interaction with the time fields with the gravitational field. So essentially, we have this collapse, and so we can create a microscopic level microcircuits, I call it, reversible time. So it is the value of that is 10 to the power minus 24 seconds. So only at that level it is really reversible, and corresponds to about 10 to the minus 16 meters, which is the Bohr radius type of thing, classical radius to uh, you know uh, to the broad radius regime. So it is in the electrons aspect, which is the most fundamental aspect. If you talk about Dirac, anybody, the electron is the most fundamental particle ever since Rutherford, right, showed by experiments. So then you show that macroscopically, the macrocircuits have irreversible time. So we cannot reverse time macroscopically. That's clear. But the microscopically, they have some reversibility aspects. That's what I'm going to bring out here. So essentially, if we go here, supraluminar, so essentially it covers that plutonium, So it doesn't violate general relativity or quantum mechanics by any means, but it is an emergent property. More detailed analysis and the mechanism that brings out that. So we have to look into that. So essentially, start with discrete. So for this, we need a discrete Lagrangian, and and that starts with the scalar field. We know everything starts with potential or fields, and we introduce local potential, which is created by this process of the uh, massless bending plus the hot PDP mechanism creates a local potential, which is which has phi square and phi power 4 relationship. So it is non-linear. It's not a linear relationship, a linear potential, and that's the key thing. So from this, we can create a discrete action based on all this literature, and I will show you briefly all the literature exists at the end of this uh, presentation, the paper or the article. So you have all the papers here, literature. It's mostly literature about of quantum cosmology, essentially. Okay, so you have the discrete. This is the important aspect, the discrete. So you can discretize the action, which is based on the originally Schrodinger equation. Then it changes to uh, discretization or numerical analysis. So I talked with regards to numerical relativity, and that's upcoming because it shows a memory. The space time has memory. The numerical relativity that people are explored uh, is the one that has shown this. So these are very important because how that gravitation wave relates and and the retention of gravitation wave, things like that are very, very important. So that's where the lattice formation and later on the defect formation. The defects are what is creating the irreversibility, and this will be brought out in this paper as well. Okay, so here denote finite difference, and so we are essentially a finite difference aspect. We are, you know, numerating the action, the closed form. And the same way it was numerated Einstein relativity, which only short-sized metric could really solve the problem. But then with the numerical relativity, discretizing that helps to understand more with a very careful thing. Of course, we cannot lose the physics of it. The physics is in the closed form, but we can retain all of that by a very careful numeration process. So that's what it is. Okay, so discrete Euler-Lagrange equation, which is a fundamental thing, uh, helps us doing that. So I'm guys going to go through that and I'll refer to this paper to get more details. So essentially what we are saying is that by this numeration, we show that we, the space-time could be encoded, something called the quantum cellular automata. Um, so it has, we start with this potential and then convert to a local energy density. It's very important. We know that vacuum energy density is the fundamental thing that, that doesn't change but we can see that many other changes because the vacuum itself is very dynamic. It's a dynamically produced. Vacuum is dynamic. That's the key aspect comes about. The luminar aspect comes from the superluminar aspect. So it's a derivation of that. And so it's dynamic. So vacuum is dynamic, it's created. And then from the vacuum, then we have subluminar, real universe that we live in. And that's all because of gravity. Gravity is bringing down, as we know, it forms black holes or micro black holes, which can grow into massive black holes, and then that will you know reduce the speed and bring everything to you know at rest. And then, of course, we have to contend with dark matter, dark energy, things like that, which are all done here in brief. And there'll be a paper that's next one that I'm preparing that talks about how the hadron lattice is, creates the universe with the defects and other things, and then it advances towards understanding about time itself. Okay, and the later papers talks about the asymmetry, the irreversibility, and the heterogeneity of the universe. So it's all created from these random fluctuations. Okay, to start with. Okay, on the lattice, the particle formation is triggered by a local threshold rule. So we have this rule that we develop essentially becomes so it's a 0 and 1 like binary. So you have zero signal because essentially the superluminal thing is noise. So it has, in terms of signal level, signal to noise, pretty close to zero. But when we create a particle in the local level, the signal starts, almost like a Diracian a type of signal uh, noise ratio occurs, and then that's where the formation of particles. So it's a spectrum that we can. It's very difficult to analyze that with the existing theory because much higher energies are necessary for LHEC. But I do provide in many of these uh, publications, there is a laptop experiment we can conduct that can that can do very similar thing like LHC. So LHC now is limited by the energy that it can achieve, but in the future it could be using that. We may get to that level, but in the meantime, much cheaper and uh, economically possible laptop experiments also can show these uh, effects and prove many of these theories. So it shows that a binary automaton variable. So it's an element of 0 and 1, which is a binary. So A is the key thing, the threshold. The density is this local energy density in terms of the A of x of t, which is a binary. And the rule is local, causal, and compatible with lattice field theory, continuous dynamic. So it is, we have to also rationalize why it looks like a continuous thing, although locally it is discontinuous. And then I work with Emery, and we have published papers that actually, if we look at the signals, the local level, sinusoidal, they are discontinuous, but they're so small that it get uh, spread out and becomes looks like continuous. It's the same theory that we can talk about lasers. If you look at the original way, the sodium vapor lamp experiments showed that we see a continuous line, but actually, if you increase the resolution, we can see the two lines, close lines, and these are the one of the proofs of the quantum theory, that you have a clear distinction between the uh, two characteristic wavelengths. So that is what helped to create the lasers at the quantum level, and we have the quantum diodes and things like that, which does more in the electronic regime, and eventually quantum computing, which talks about superposition, entanglement, so on and so forth. But of course, the noise is the biggest problem. So one of the things I will note here is that uh, as soon as an environment is introduced, it decohers that. The entanglement goes away immediately. So you have to keep it away from the environment, which is the pure state, what we call pure state, in order to achieve that ultimate secure. So quantum computing is trying to resolve that problem. So this is applicable to quantum computing as well. These theories, quantum, uh, you know, cellular automata becomes a very important part in that. So binary bit replaced by qubit, like I mentioned. So we can have the binary 0 and 1 to a qubit, which has uh, c squared, means it has an imaginary aspect to it. So here the 0 represents vacuum and 1 represents the particle. So 0 and 1 in the binary level. Now everything can be reduced to a binary level, and that's the important aspect one has to uh, confound. Um, okay, so now we have, you can talk, I'll go right into it. So this is consistent with lattice quantum field theory as well. So there is no real violation of any rules, but it's an advancement that shows that we have to see it more in more resolved levels when we can see these things. So entanglement, entropy, and emergent reversibility. So we have to prove how it become reversible, and that's what is shown here. Uh, so to quantify local complexity reversibility, it is coarse-grained entropy like function that's defined at lattice level. So the quantum lattice level, we can define a function which is given by that, and all this literature uh, gives you all the details about how this is done. So the local entropy, complexity, the density, it's a function of phi x t square, and we know that that comes here in our original definition of the potential. So it essentially uses that, and it's a continuous derivation. So it's a very easily derived quantity. So mathematically derived, derived mathematically. Uh, Manipulation of mathematics. So it's a natural mathematical physics. Okay, so then in order to simulate that, we use this size of the lattice, and lattice size of all these specifications of the time horizon 300, spatial step zero point 0.1. So in order to create a graphical output, we need this Python programming and you know the artificial intelligence to some degree, and you get the graphing of these simulation parameters. So we can simulate that and show how it works, and that will be shown now. So overall computation scale, we know now these days we have to worry about the complexity scales in order of T to T, so that we can get it within the time frame that we have. So this is one of the big aspects, as we know people are trying to reduce this uh, as we as we talk about more and more quantum computing, artificial intelligence, things like that. Uh, so we create the heat maps and all that, which I will be showing. So the methodology is a unified framework which establishes microscopic dynamics, reversible and variational. Macroscopic particle like etc. emerge via Lafayette thresholds. Entropy goes. So the entropy makes it uh, immediately entropy happens as soon as you introduce the environment. And the environment, you cannot prevent that. And we know that many of our tests, we isolate the environment and create a local environment with a vacuum or anything, a vacuum chamber, for example, created. So the normal environment is removed, and we can reduce the vacuum to extremely small levels, 10 to the power minus 22 or things like that, which I have used for scanning electron microscopes and things like that. So and transmission. So where we can look at the interaction of electron fields and the matter in terms of understand the vacancies or defects, things like that, dislocations, things like that. So, so it's a lattice quantum field theory. So the lattice is very important because we do see structure in the universe, and the structure eventually becomes like a lattice in our real materials. If you look at the any materials like a body-centered cubic or the seven crystal system or face-centered cubic, things like that. Iron itself has this BCC structure or BCT structure, um, tetragonal structure. So even a diamond has a tetragonal. We know that. So these structures are very important. The crystal structures are very important for real matter. So that's something we have to always keep in mind. So scale dependent transition. So how does it happen? So we use the fundamental theories of the matrix. So we have the U and rho and U plus because this is a matrix we talk about. So we have to do the matrix operations, and you have the evolution aspects, things like that. When we put in there, we get von Neumann entropy. So it's like von Neumann entropy, but so these are fundamental aspects. Unitary invariance. So invariance aspect is again important in all of the uh, symmetry and spatial geometry. Okay. So then we plot it. So I don't go into details of the derivation, which I have, and all of it I didn't publish because it is so enormous. But if somebody needs that, I can always provide that. Uh, so a dependent micro macro crossover. So We use all these discrete Lagrangian and this operation, matrix operations, and finally, when you put them together, we get this plot of entropy versus coarse grain length. So we know there is a crossover 10 to power between 10 to minus 16 and 10 to power 15 where the crossover occurs. So this is where the microscope reversibility becomes microscopic irreversibility. So that's a very important range, which happens to be in the the electron's size or the size of the electron, which is sub atomic level. Uh, so we know lattices are there. The lattices normally we see, in a crystal, like even iron, for example, single crystal of iron, if you can make it. It's very hard to make that, but we know single crystal of silicon and other things. If you look at the atomic structure, the atoms are arranged in certain patterns, which we call the geometry of the space. So there are seven crystal systems, like it could be body centered cubic with a certain direction of the plane, and it's cut along the direction of the plane to get the maximum electronic properties. So all the integrated circuits, even using all the modern computers, had to use these aspects, and then you adopt the silicon or the single crystals to create the avalanche of electrons that can act as amplifiers or resistors and capacitors or even inductors. So it's a solid state device that's used now. And this essentially means that we are talking in that region of subatomic aspects. So this is where things are happening. Uh, but when the macroscopic level, you have the environment coming into picture, it totally decoheres everything. And we don't, the reversibility cannot occur. And that's what the next step is proving. So essentially, all this mathematics is necessary to uh, prove thoroughly how it works. So it's a very extensive and completely understandable proof that that can create uh, what was necessary to uh, prove that aspect. Okay, let me get this straightened out. Okay. All right. So let me ensure something here. Okay. Okay. I have to ensure something here before I can. All right. Give me a minute. Excuse me. There's something in the computer that's showing up. All right. So now, all right. So the important thing is that the act as non-unitary circuit, transforming the evolution map completely positive, trace preserving channel. So these are some of the details. Um, Essentially, we are saying that uh, measurement induced phase shift. So the measurements can induce this non-reversibility as well. So that's shown here. So measurement induced microscopic irreversibility. So these are the reasons we cannot see the reversibility. In a normal thing, we cannot see the time reversibility at this microscopic level. We cannot see because, like a Schrodinger cat paradox, as soon as we open, it becomes entangled with the environment, it loses the purity, and then it will decoher. So it becomes noise. So that makes it irreversible. So measurement acts as a macroscopic element, breaking time reversal symmetry and generating arrow of time, which is entropic, based on entropic aspects. So these are all fitting together very carefully. So the cross gaining, these are understood from uh, literature as well. So the evolution happens for the lattice wave function. The famous the normal exponential I theta xy. Uh, so when we use all that, we can plot emergent phase defects in 2D microscope. So essentially to prove that, and that's very important, the defects are the ones that's locking in the mechanism. So this one we can show that uh, in the evolution, the defects automatically come into picture, and mainly it is because the pure state of particle, and then you introduce the environment, it creates the decoherence, entropy, which then creates the defects, and that locks in the thing. So it is a vicious circle that goes on to create that irreversibility, and that's how matter. Otherwise, there will be no universe, right? Because you are and there is no as long there is no asymmetry, the matter antimatter asymmetry. We cannot have the baryons, and then we may not exist if it's not for this simple purpose. Uh, in a strange way, we exist because of the defects, and that's very strange. I mean, even our heart has a beating rhythm. If you cannot have perfect signals, right, then we cannot exist. So the beats in the signal itself, one of the proofs that we have these, imperfect or defect aspects. And as a material scientist, I learned a lot about that dislocations, vacancies, interstitial, which form the core of how everything evolves. And then we exist because of that. Even life exists because of this region. Uh, so in any case, continuing with our analysis, we have the defects that forms and the unitary microscopic evolution based on this careful matrix analysis. We can show again that spatial blocks can exist, the effective macroscopic map we can do, data processing, things like that. So we go through all these uh, mathematical manipulations in order to prove that in the microcircuit, this is unitary, this U rho n is the energy density, U plus is unitary reversible. But the transition happens because information loss. So it's associated with information loss, which creates because of the entropic nature that's introduced by the environment. Macrocircuit completely positive trace preserving irreversibility of this. And essentially, these are all entropic aspects. So we talk about Shannon entropy versus Von entropy things. I'm not going to go into details about that, but these details help us more find proofs of this. So essentially, we know that Lyapunov indicator is the one that indicates the disturbance or the uh, or the chaotic aspects that's created within a very smooth scheme. So it's used very well in fluid dynamics, things like that. But this is a very important indicator, and we're using these aspects. We can prove that how that discrete time evolution happens, and uh, and then I describe here why it's unitary by using this careful mathematical proof that uh, the reversibility happens, the absence of chaos, can happen because of special conditions that occur within that. But in the macro circuit, we don't have, we, introduction of this K alpha, which is partly due to the environment, and the environment creates this irreversible aspect. Okay, so monopole include what? So now we include that all the defects, which are generally called as topological defects. So it belongs to monopole like point defects, not at phase rules, not at phase tubes. So these are topological defects. Um, so singularities kind of can be explained on the basis of that. So cosmic string models, things like that. So when you put them together, we see the vortex lines, monopole, random circuits. You see that it is ingrained in part of the whole quantum lattice. So any lattice, we look at that, and we know that defects occur, uh, like dislocations and point defects. Then you have the vacancies, interstitial, and that's what it makes the crystal dynamic. Otherwise, the the bond strength and things will be so high you couldn't have made any iron structural materials. It's all possible because of this defect, uh, defect defects in solids. It's a very important part. So the three-dimensional things, you have this unitary evolution, no stable phase singularities form. When microscopic elements measurement induce decoherence, topological defects stabilize as vortex-line monopole-like structures, providing persistent, irreversible macroscopic degrees of freedom. So, so topological defects act as persistent macroscopic memory, which we proved from numerical relativity as well. So there is a connection there, quantum mechanics and the light connection between the quantum mechanics and the general relativity there. Maybe that will resolve the problem of these eventually the vacuum catastrophe and things like that. Define cosmological era of time. So uh, emergent particle formation 1D and 2D. So in terms of I just want to make a side comment about vacuum catastrophe. And that may be because of the defect aspect, the entropy, because we are not taken into account the defect aspects. If we talk about quantum defects uh, and the memory aspect from the space time, from the numerical relativity, and we already have the discrete Lagrangian we considered here. So essentially, we have discretized the Schrodinger equation as well eventually. And so if you discretize the Schrodinger equation, and then discretize the general relativity, maybe we can prove that they kind of come together, and thus we have quantum gravity uh, fairly established. So, but that's a long way. These are the steps. These are probably the components or the piece of the puzzle that will help in that. Uh, Particle events. So now we can see how the quantum cellular automata particle formation map occurs. Particle 1D in one-dimensional aspect, emergent high energy regions from reversible microscopic dynamics, coarse grain criteria. So we talked about that already. So from there, if we map it, you can see that we can see the stream of particles coming up. So it is proven from theory itself that you can create this one. It doesn't assume anything other than discretizing, action. So then we can prove that. So the color scale is dark zero, local energy density. So if it's a zero, dark gray, no particle formation. If the energy density greater than a critical energy density particle forms, and that you have the bright spots here where the particles are forming. So there you have densities are much higher. Then you have localized field excitation, lattice center, where phi equal to you know 1. Okay, so we have consistent. It's all derived from the derived fundamentally derived equations, and it is mapped, and it shows clearly that indeed we can get the microscopic reversibility and macroscopic aspects, uh, visual aspects we are getting about that. All right. So, okay. So let me go back here. So essentially, what we are proving is that the fields, we plot the fields, the particles, and the entropy. So we get, so also it's botched out because of the particular way resolution sector. So we can only show like that in terms of the colors, uh, but it does show the microscopic reversibility and then eventual entropy production, which makes it irreversible. Right. So the macroscopic aspect transition to microscopic aspect. So we already showed uh, the transition aspects here, how the transits, the entropy increases, and that makes it irreversible. So essentially, it all puts together, totally consistent manner. So we have the simulation details. Okay, so now we have the field evolution, particle formations in terms of time, and then the entropy, how they all fit together. Uh, so how the propagation occurs. So it's very clear there. So the field. So this is a in 2D. We have these fields that forms, and then as bright spot, like a star, they start increasing. The particle formation then, and entanglement entropy proxy. Uh, so they are all clear. The nonlinear aspect from the potential that we talked about, discrete, and the entropic measure, which captures, you have the von Neumann entropy as well as Shannon entropy, specific aspects. So they are fit together very well. So the color map and that shows the how the entanglement can occur. The entanglement we can talk about particle, pure particles entangled with, but when put a pure particle entangles with the environment, you have the decoherence happening. But if they entangle with each other and without environment, then they have the coherence. So the coherence versus decoherence is one of the key aspects. Uh, Couple lattice systems emerge and collapse. But when you talk about entanglement, no, usually we talk about coherence, like in lasers and things like that. So we distinguish that. So again, it's more detailed about that. Simulation parameters. Uh, Again, I talk about gravity. So finally, final state of two lattice. So you can see in the space time, these are all spread out. Density field and the gravitational potential and the collapse regions. So you have the collapse regions. Collapse regions. So, for example, galaxy seeds, they can be seen as galaxy seeds. So when it is greater than certain level, lattice size, local over density exceeds critical threshold, and white pixels indicate collapse regions, which serve as precursors microscopic, while black pixels indicate under threshold condition. So you are under threshold. So you can kind of connect with dark matter, dark energy type of thing eventually with these maps. So the galaxy seeds, how they form and how they grow, things like that, and then propagate uh, can be understood from this. So these are initial aspects to understand how the galaxy formations. Uh, Orthogonal planar final density field obtained from discrete non-linear teaching governed by continuity equation coupled to Poisson equation. So we put all this together, high density regions, bright colors, you can see, indicate nonlinear amplification over density, where darkened regions correspond to underdense voids. So you have voids in there. So emergence of compact, spatially localized, high density reflects gravitational collapse beyond a critical overdensity. So how the gravity, so then we talk about micro black hole formation, black holes, things like that, and also these things indicate how the dark matter, dark energy comes into picture in our actual cosmological considerations. Okay, so essentially we talk about emergent particle formation, entropy, God. So you have the scalar field evolution, emergent particles, and then average entropy proxy over lattice. So uh, how is discretized nonlinear Klein-Gordon dynamics, chaotic self-interaction. So you can see now the variation of the entropy itself within the lattice structure. Lattice, we are talking about hadron. Eventually, in the next paper, I'll bring out the aspect of hadron lattice, that this protonic structure eventually forms like a lattice, and this lattice then has defects in them that makes it that locks in the mechanism so that baryonic asymmetry is established, and then it can grow and it creates the galaxy seeds like I showed you, and then that grows to create the real universe all the way to uh, live universe or life. And of course life depends on the parity. The chirality is very important because if we talk about the carbon aspects, the carbon, how carbon is the most important aspect as far as our lives are concerned, how the carbon and hydrogen come together, and that eventually creates the organic matter uh, that that is the fundamental basis for all the life. Uh, Microscopic region, observable time event microcircuitry, and okay, so Lorentz violation discreteness. The higher order spatial derivative introduce control Lorentz violating corrections, small scale. So that we talked about also the early universe thing that I started. That's a fundamental thing. So essentially, we look into that the future aspects, fully quantum extensions, quantum fermions, topology. These are things we can do, and then we talk about also even machine learning and things that can be introduced, uh, and some of the ways we can detect uh, by gauge field. We can use Newman entropy, uh, scaling theory, computation information theory. Okay, so you can use computation aspects. So some of the limitations that I talk about can be overcome to prove that. And the experimental aspects also I'll be looking into more. And the previous publication I talked about the experimental aspects. These more theoretical aspects which proves that thing. But in the next papers also, I bring out how you can experimentally uh, on the laptop on the lab uh, based experiments, tabletop experiments you can conduct uh, apart from uh, the normal uh, LHC type missions, right? So So let me go into one of the, excuse me, uh, one of the things that I talked about. Sorry, is the so one of the important things that came up is this scientists trying proof time travel is real and happening now. Okay, sorry, this one is, I have to get rid of this one. Okay. All right. So physics have so this is the most one of the most recent literature. Physics have demonstrated waves can bounce off boundaries in time, not just in space. And let's see how can I get rid of anyway. Time reverse copies of the original. So you can see that time reverse copies of the original can be developed. Closest laboratory proof yet manipulating flow of time is physically real. No one is sending people into the past. The results challenge basic assumptions about how time operates and open practical doors in quantum sensing and signal processing. So you have the metamaterials that reflect waves in time. So this is published in Nature Physics. It's a time reverse copy of the original. So you can see it kind of at least partially prove my time reversal that I showed now, this paper. So it's a partial proof of this paper itself, carried experimental proof in a way. So already it exists now. Carried the same spatial information, propagated back through the time dimension. So I don't know, I can get rid of this one.
Yeah, but what does that mean, though, Rajan? I mean,
Yeah. Okay. So
because
they
you know the way you have like some particle or something, and it's moving forward, or and then it hits something,
he,
and then it bounces back, and the path it travels back is in reverse. Yeah,
yeah.
but that doesn't mean time is reversed, is it?
Yeah, we can watch this video maybe 1 minute. It may
Sure.
give some.
Yeah, I don't really understand that, to be honest. But is there sound on that video, Rajan? Hello. Can you hear me? No.
I'll just move it further.
Uh, Rajan. Hello.
Ah, yes.
There's no sound on that video.
Let me let me move this.
Do I have to enable sound for you or something?
Yeah. So what time travel actually means a lab. So I think they describe the archive and things like that, and the physical review A, so which is the top journal. Uh, Experiments on superluminal light pulse propagation. Media have shown that a pulse. So already superluminal thing is coming there, right? So our theory is is okay. What it's based on the superluminal aspect. So they are studying that.
Well, how is
So
their
they
wave superluminal though? Is it a wave packet or something?
so light pulse propagation is superluminal.
Or how is it
So they are
superluminal? I thought they were saying that's impossible.
But now they're saying that experiments of superluminal light pulse propagation. We have to look into the uh, actual papers, but it's a
Yeah.
light pulse propagation. The
Well,
anomalous
maybe I
dispersion
mean there's
media.
a thing where you can have the wave packet or something can move faster than the particle or something. So if the
Yeah.
particle's moving
So
at
there's
light speed,
it depends on the media. It's called the anomalous dispersion media, and
oh,
we have to look into that. So in that media, it depends on the medium of travel, right? How the signals travel. So in this anomalous dispersion media, it can travel faster than speed of light.
so it's some
So
sort
we
of
have to look at
metamaterial, is it?
yeah, it's a something that something that allows that. We have to look into that. What that is
Okay.
physical review paper. So I don't know whether
So if it's
let me
traveling
see whether
faster than the speed of light, is it already traveling backwards in time? Or
yeah. See, this shows anomalous dispersion superluminal light pulse propagation negative group velocity. So this
group
is a
velocity?
paper in physical review. So physical review means it is already established. It's already accepted
All
by
right, but
the
it's that's been well known that group velocity can be higher than the velocity of
yeah
the group velocity of the wave packet is higher than
yeah
the particle. So that's not new.
yeah.
It'd
It's
be interesting though.
actually tachyonic theory that George Sudarshan Dal showed is essentially that it's a group velocity can be faster. So this is, but they're using that aspect here. That's all.
Yeah,
They're using that uh,
it'd be
essentially
interesting.
bringing
To know if
out,
that,
yeah,
it'd be
bringing out
interesting
that
to know if
aspect.
that it'd be interesting to know if that connects to your work with this or
Yeah,
superluminal, or is it
yeah,
different, or are they
yeah.
connected?
The falsibility aspect of our theory is proven here. It shows that yes, it is well within the theory of relativity. It doesn't violate that. And the superluminal aspect is our main thing, right? The main thing is that everything started as superluminal condensate. And this one says, yes, it's possible, right?
Yeah,
It
well,
doesn't violate
yeah,
that.
the group velocity thing. I mean, how much
Yeah.
faster? Because you're the superluminal thing in yourself and Emmanuel's work is can be many
About twice
orders
the speed
of
of
times
light.
faster. It would be like
About
very superluminal. I just think they might be two different things, but yeah, yeah, true enough. Anyway, I don't think. Yeah, yeah, I think the superluminal thing in the condensate sounds valid anyway, but it might be. I'm just thinking it might be a different mechanism to this thing.
yeah. Because there you have monopoles and things like that, and then that gives the energy. But it is cogmare. It is a noise. It is a very it's a immeasurable thing.
Right.
Uh, you cannot measure that superluminal thing in that phase. That phase cannot be measured realistically because there's it's like dark matter, even more than dark energy, maybe the most primordial aspects from which the dark energy came into being. Because even dark energy will be detectable if you can prove the WIMP, the weakly interactive massive, particle of the gravity, because that aspect is very gravitation aspect, right? The dark energy, dark matter is a gravitational aspect rather than the electromagnetic aspects. But this is more fundamental than electromagnetism or gravity. It's the most primordial thing, the superluminal condensate. So it is there everywhere in our thing, the noise, but we cannot measure it and we cannot detect it. So we don't see it. But everything evolves from it's everywhere. We are covered. We are inside of that. It's all around us, in us, everywhere.
Okay, but what if it turns out there is no graviton? Is how does that affect your theory?
Gravitons are not necessary actually. The
Oh,
supernova. In my theory, it's not necessary. It's a time. It's a mechanism that happens. It's a localization of the monopoles which creates these dipoles,
yeah.
and these dipoles then creates a condition for massless bending. The massless bending creates the gravity, and and hence the gravity then creates the particles, the microparticles and the particles.
Okay, there's also
And
point to
that's
the
it.
whole discretization of
Yeah,
space-time.
yeah. So by discretization, coarse graining of the space, we can show that. So the numerical relativity. So
Is
like I
that not
said,
discretizing space-time, not essentially looking for the graviton?
well, you can. I mean, you can. And I showed you a spectroscopy where, in order to create the graviton, you need certain energy, certain level. And in one of the papers, I show spin spectroscopy.
Didn't Feynman already do the discretization of space-time?
Yeah, the discrete. We have to go into that. We have to resolve it, right? We have to go into more and more solutions in order to
Yeah.
see that.
Well, there
So
was a
in
guy,
order to resolve,
I think it was maybe Kurt J. Mungle or someone like that, and he was on talking about how they didn't need a theory of quantum gravity or something because Feynman had already discretized space-time back in the whatever 40s or whatever, and or even earlier maybe. But I wasn't that convinced about everything he was saying because he's he was talking about, right, we have like this massless spin 2 particle that's all related to well where they get the spin 2 from, but I'd have to go back and watch it, but I wasn't like thoroughly convinced by his arguments because I thought there's a bit more to the whole graviton and our unification of the fields. I don't think just because you discretize something, it means you've unified everything or anything. And then he was also giving out about how, these unification things aren't proper unification theories from the point of view of like a quantum physicist or something, because like if they want to unify, he was a little bit contradictory because he said, well, if you look at you want a group structure to unify everything, but you want a single group structure, not like in the standard model where you have SU3 cross SU2 cross U1 or whatever, because that's three different things mixed together. So it's a mixing rather than a unification, he was saying. But at the same time, he was speaking then before that of, let's say, Faraday or Maxwell's unification of electricity and magnetism that became under a single group, which was just U1, yeah? But then, but then he seemed to contradict himself by saying that wasn't a real unification either because something, but it was like, but that is unifying two things under a single group. So why isn't that a unification? And
but that unified the electric and magnetic fields, right? Electric and magnetic fields is unified into light and the light, but the gravity is not there in that, right?
No, but I'm just talking about the fact that they unify. It's still a unification theory of electricity and magnetism under a single group. So that should be considered a unified field. But he said it wasn't, even though it seemed to. It had all the proper fundamentals necessary for it to be a unified field theory of electricity and magnetism. Maybe they're not. I suppose those aren't fundamental forces, but they're only not fundamental forces because they've been unified, isn't it? Do you know what I mean? So, I mean, if you were to unify the other four fundamental forces, then those wouldn't be fundamental either, would they? Because you've unified them into a single field.
That's the subset of that. It will be subset of the unified theory.
Exactly. So, but then you can't say that. So then you can do the same thing with electricity and magnetism. Say they're a subset of the unified electromagnetic field. So, yeah. So, I just think. Anyway, that was just an observation there. So I don't think we really I don't think we really understood this thing. It seems to be even more complicated by the idea it's superluminal. So it's already, if it's going faster than the speed of light, it could be going backwards in time anyway. And now it's being reflected and going back in time. Like if you think about a wave like a wave in the ocean that comes in and bounces off a wall and then goes back out. I mean, if you were to play that backwards or forwards, it would look the same either direction. You know, that kind of way.
Hmm.
Obviously, there might be an issue with the splash or whatever, but if we were to remove that, if it was just like a no splash situation. So
Hmm.
when you say, okay, the wave goes back out, it looks the same as when it came in. Does that mean time is reversing? I don't think so. I don't know how they I don't know how they can justify that. Really, to be honest with you.
Yeah,
And I
you
would
see
say
that this is
I would say
exactly
that's
the
a bit
way I
controversial
see
anyway.
it.
Like they can, you can say, oh, it's in a good journal, like what was it, Nature or whatever. But
Nature and physical review. Eh.
yeah, so you can say that, but that doesn't mean. I mean, that whole um, that whole proposition
You
that time can flow
see,
backwards, or
yeah,
that
they say that
interpretation.
makes a
Wait,
copies.
can I
Just
speak?
take the copy.
So,
Yeah,
wait a
please.
second. Just let me finish my sentence.
Okay. Okay.
That whole thing is sorry, is, you know, that interpretation even is controversial within physics fields. So it doesn't matter if it's like, I guess you know, like it doesn't mean that it's a done thing. Like it's absolutely correct. It's just, do you know what I mean?
Yeah.
Uh,
Yeah.
well,
I
yeah,
mean, it's an evolving thing. It is not fully proven. I agree that we are on that way. We are making a piece of puzzle, but it doesn't mean that puzzle is solved yet. You know,
oh no, I'm not
we are
saying
just
that.
piece.
I just mean that even, you know, if they make a claim like that and the claim is still disputed, then they should either they should be making allowances for that and saying, well, that this is how we are interpreting it through this lens, but through a different lens, it could be some other way. But then, if that other way is just the conventional way that we view time and space and events, then that sounds like a pretty big deal because, you know, one is simpler and kind of reflects why we normally see the universe, and the other is a lot weirder and doesn't seem to make a lot of sense. So if you have some sort of wave flowing backwards in time while time is still flowing forwards, I don't know. I mean, it just seems like it's missing a very fundamental um, sort of, you know, a fundamental understanding of the universe and how it works on a basic philosophical level. Like it's devoid of a certain philosophical sensibility, if you like. Um, but yeah, so you need to know how to justify what they're saying. Well, it's not your responsibility to do that though, or they need to justify it. Maybe they do in that article, but I don't know if you want to continue reading or what do you think?
Yeah. So one of the things I just make a comment of your thing. So
Okay.
essentially, you are talking about Newtonian physics. So the classical physics, Newtonian.
Yeah.
Anything more than that is not allowable in that sense because you are talking about simplest aspect is the Newtonian aspect. You know, is the classical
Well, this
physics
is
is the
like
simplest thing.
Newtonian and classical here on in this particular instance. We're just talking about like how things appear in reality. You know, obviously, if we're
Huh?
going down into like a quantum scale or whatever, um, you could say things are behaving differently down there. And
Yeah, that's
I
a
grant that there are certain things that are a bit weird there. I'm not saying that it's classical all the way down or
yeah.
anything, but I'm just saying, well, you know what I'm saying.
Yeah, that's exactly
There
what
is
it is.
like
I mean,
there is some people who say that there's still like a classical thing. There's a classical interpretation, isn't there? There's like pilot wave
yeah,
theory and different things. So if those can be equally applied and give equally valid results generally. I know that some people say, well, you can't use pilot wave theory, for example, because of so maybe determinacy or something. How's the particle determined to be in the place it's in, or there is like a comeback to that. But even so, I don't think you need to rest even on pilot wave theory, but something like that, you know, could be
yeah.
a
So in a
solution.
simple way, you have classical physics, which is what we in our real universe we see with our eyes and everything. But we
Yeah.
got to quantum scale, things are different. That's exactly what this is. What's happening
Yeah.
in the
Okay.
quantum scale.
I agree. Maybe they're different, but different. I know that they say, "Oh, no one can understand quantum mechanics," and anyone who says they do is lying, and that's fine. But if you're going to be talking about it at all and making uh, either predictions or just definite statements and conclusions about what is going on at that level, those things need to be at least logically consistent within their own framework. Otherwise, they cannot be spoken about at all. And what I'm looking at here, I'm just trying to understand how they're even making any of these claims about a particle going backwards in time. I suppose Feynman used to do that, didn't he? Where you'd have like
Yeah.
particle pair production, and he would say that the matter particle is going off forward in time, but that the antimatter particle had come backwards in time to to cause the annihilation. But I think that might I think that might be a theory in itself. I don't know if that's provable or proven or provable. And if they're going off that, then to state whatever they're stating here, it seems more
Mhm.
like a kind of a fiction or a delusion that they're having, like a fun game they're playing. But I don't know if it's how you would justify it. And since there seems to be I wouldn't even call it classical, I would just call it common sense. If there's a more common sense approach to what's going on, then that should be the one that's used. And then again, this is a kind of a pop sci article. We're not actually reading the papers, so maybe we're just getting
Yeah.
a
So this
sensation.
is
Yeah.
because it will take a long time to understand the actual, because it'll be involving a lot of mathematics, things like that. So this is a simpler version of understanding. So it says that equations, they could be trapped in deep structure and feature of physical law. Equations governing fields and particles are often symmetric under time reversal, even though our everyday experience is not. In this view, a time interface engineered in a transmission line vibratingly becomes a concrete, tunable environment where those hidden symmetries are briefly exposed, harnessed. So it is a tunable, we are getting a coherent things, and that only we can figure out these things. Uh, so instead of merely watching entropy march forward, researchers can flip the script carefully prepared waves, forcing them to retrace their histories while still respecting causality and thermodynamics at a larger scale. So I think this is fairly reasonable. So I look at it as fairly reasonable. Because larger scale, you have
Well, I mean,
causality
it
and
doesn't really say
thermodynamics,
anything. Like
right?
if I drop some, like let's say I drop something in a pool of water with a circular boundary around the outside, and then we have entropy. The wave flows out, hits the
Uh-huh.
boundary wall, and then all the waves move back in and converge towards the center point and reverse the process. But now it pops up. What the thing about that is, it looks like there's been a reversal of entropy, but actually there hasn't been. It's still a forward moving entropy thing. It is interesting, but I would like how are they justifying what they're saying that it's actually entropy reversing? I mean, and not just what I mean. I'm not even sure. I'm not even sure that I would agree with them on that fundamental level of how they're even measuring entropy, or that it's not just
I mean,
like there's lots of
you are not,
examples. There's lots of examples of entropy going in reverse in our universe. For example, the fact that stars form or galaxies form, but we don't say that time is going in reverse just because we have a definition that uh, the arrow of time always moves forward in the direction of entropy. So
Mhm.
it's just irritating me unless they can show that something like the energy is being conserved in like some sort of not enthalpic, but like the way like there'd be a loss of energy in an entropic system, even if it looked like it was going backwards, the arrow of time is still going forwards, so entropy is still increasing, then even after the system collapses back in on itself, the energy would be lost. So we would say, well, entropy still occurred, time is still moving forward. So unless they can show that all the energy was actually recombined within the system somehow, and there was no loss of energy, which should seemingly break the laws of thermodynamics. But they're saying explicitly that it is still respecting causality in thermodynamics, although it does say at a larger scale. So presumably it's saying that it's breaking thermodynamics at a smaller scale. So yeah, that's interesting, isn't it? So I wonder at what point do these laws come into effect then? If there's a certain boundary when we go down and you could have like infinite energy or something like that. Are they saying that?
Yeah, actually, there's another article, ResearchGate. I don't know whether you went through that. I don't know whether I can pull up.
Go ahead.
Where I don't know whether that's still there. So here, yeah, this is one of them. Okay, what they're saying is that, okay, they're saying that the entropy thing they're talking about for the entropy does not match the experiment. So I don't know. I didn't go into detail about that, but
yeah,
this is one of the fundamental thermodynamic equation, right? For the entropy, ds equal dq over t. They're questioning all this stuff where they derive so this is the definition of entropy. Okay, S is the entropy and Q is the heat. So it's defined as dq over T. That's what entropy is. That's a fundamental thing in thermodynamics. Everything starts from there.
You have temperature and you have heat, is it? That's two different things.
This is the absolute temperature. T is absolute temperature.
Yeah.
And Q is the heat.
Right.
I mean, I you know, when I started thermodynamics in my undergraduate level, this is one of the fundamental equation. Is S equal to this thing? They say so the correct way is ds equal dq over t. Of course, I did graduate level thermodynamics, everything highest level.
Yeah, I recognize that. That's I know about that. Okay, so pretty basic, but so they say interesting. It does not match the experiment. As you've got like this interchanges between entropy, and it says is meaningless. The research paper on entropy has become a useless paper. I don't understand that. I mean,
I don't fully understand that. I didn't go into details. I don't know whether I fully agree with these things, but I think there is something that talks about, if you talk about macro thermodynamics, I think it will become clearer. In micro thermodynamics, maybe this violates that. Doesn't hold good. In macro thermodynamics, this will be okay. I mean, I can accept that. If you talk about the quantum thermodynamics, for example, there you have a different story.
So at the quantum scale, you can break those laws of thermodynamics.
Yeah. That I think it's quite reasonable. Although it needs more research, to prove that. But so from this point of view, they have to qualify the statement. They cannot say a general statement like what they have said. I don't agree with that. So I don't agree with the address useless. That's a very general statement. I don't agree with that. You have to qualify the statement.
It's strange kind of language as well to say meaningless.
Yeah, people go all the way to the other side of the thing. You cannot do that. You have to qualify the statement and say, under these conditions, yes. Under the other conditions, yes. That's how everything should work. But they are going,
Well, I mean, if they have an equation, right, and the equation doesn't work or something, then it's valid to say, though, this is meaningless. But it's kind of a weird way of saying it. But there's nothing too wrong with it, as long as if they're right, then that's okay, I think. But you're saying something else, I think, Rajan, aren't you? That it's like they seem to be going the other way, like too far in the other direction, meaning
Yeah,
they
exactly.
should throw entropy out entirely,
Yeah.
like
You cannot
beyond
throw the
the
baby out of the bath, right? It's like throwing it's like quantum mechanics, everything is wrong. Or generally, you cannot throw those. They are still but they're okay. And there is a higher level of principle, and they are subsets of that, but the subsets are still true, but they are not the what you call prime set, a primordial set, so to say, or prime set. The prime set is something else. That's what we are trying to figure out. Like quantum gravity, there may be even more primes, higher prime set than the quantum gravity itself. If we can do that,
Okay,
that will
but
be the unified
I
theory.
don't really get it though. I mean, so you're saying, how like you have a block of substance or something, you start dividing it in half, and you get down to like the smallest quantum scales, and
Uh-huh.
then there seems to be some disconnect then between the larger block, like the entropy within the larger block, and then entropy on a smaller scale. I
Uh-huh.
wonder, does it all have to be prepared? Like, if there is this like sort of discontinuum, which is what your kind of
Yeah,
research is about,
yeah,
then
yeah.
it seems like there's, it's reminding me of other research that was done. I think Sabine Hossenfelder was involved,
Uh-huh.
and so Lee Smolin's work into
Yeah,
quantum
yeah.
gravity, where they were trying to.
Uh-huh.
I have to remember the specifics, but basically, she was saying that there was some violation
Uh-huh.
in his research. It was actually in the Epstein files. Did you watch that video? It was connected.
Oh, yeah. No, I didn't
Sabine,
watch that. I saw the video. I want to watch that. See, I'm running out of time. I'm just
I
trying to
know.
catch up with time. I'm
Well,
trying to buy time, like I mentioned.
we could watch it here. Do you want to watch it?
Yeah.
Okay.
Let me go here. I don't know where. Is it here? Somewhere here.
Hey, there it is. Yeah, sure. You share it there. Go ahead. Or no, no, that's not it. But yeah, go to her channel, and I'm in the Epstein files. There it is. It's down in your recommends. Yeah, if you go down, scroll down. There it is.
That's in this one.
Yeah, I think that's it. Or maybe this is a new one. She may have done more videos on it because it's a kind of popular subject. No, this is it, I think.
Is that?
No,
No?
I don't think I can hear that, Rajan. Hello?
Can you hear now?
No,
No?
no.
You cannot hear?
No, well, I'll try and share it, will I?
Okay, sure.
Okay. Let's see if I can find the video first. What was it? Oh, yeah, I'm in the Epstein file. So it was to do with Lee Smolin wrote a letter to Jeffrey Epstein, and
Oh, he has connection.
yeah, of course, yeah,
All the people are pulled. All the big people are pulled into that now.
yeah,
The British monarchy is in shambles now because of this.
yeah. It's very interesting. He got
It's
arrested.
going to destroy the whole
Prince Andrew
prism, so to say. It's like breaking glass, of the universe.
Yeah, it's quite interesting. Did you watch the was it Pam Bondi in the there was some deposition she gave in the Senate or something, or that was
That's explosive, very explosive.
Oh yeah, it's like
I mean the news you always see this. Everyday news it is there, the world news.
Yeah.
So you cannot avoid this anymore. It's so much that you cannot even remove the image of this guy, Epstein. It's so much, it's like entrained into your brain,
Oh, yeah.
Now get rid of this bloody useless image,
Okay.
It's affecting our lives.
Can you hear
where
that?
We are trying to live.
Sorry, Rajan, can you hear that? Yeah?
I cannot hear very well either.
Oh.
Can increase the volume maybe.
Yeah, it's nearly up full.
Of my name
okay.
in Jeffrey Epstein.
Yeah.
It's a somewhat dated story and one that still pisses me off, but I'll try my
It's
best
kind of
to
choppy, but
happen there.
Sorry, what?
it's kind of choppy. But I can kind of make out.
Well, maybe
Like
if I lower it down a bit, because it could be
yeah,
flipping, you know.
introduce noise. Yeah.
Start by saying that I'm not super surprised my name appears in the Epstein files. Epstein had a well-documented interest in science in general and in the foundations of physics in particular. I spent 6 years in North America at the time when he was very active, and I personally know a bunch of people who personally knew Epstein. He was mentioned to me on various occasions as a rich guy who might potentially support the sort of research I'm interested in. I have never met Epstein. I also, to be honest, haven't followed this story in great detail. It seems clear to me that ugly things happened, and as the mother of two 15-year-old girls, stories like this hit hard. But let's have a look at the email in question. It was sent in early July 2010, around the time this photo was taken, hopefully dispelling any rumors that I'm trans.
That's bizarre, isn't it?
Oh, yeah. Yeah.
There's rumors that she's trans. Like, that's hilarious.
Just interested in physics. The email, and you can look this up online.
What? I don't get the point where it's like, yeah, I'm not trans. I'm just interested in physics. It's like it's equally hilarious.
And yourself came from Lee Smolin. I haven't seen him for a while, but he works at Perimeter Institute, and we wrote a few papers together at some point. He wrote, "Dear Jeffrey, sorry to be late replying. I've had my head buried in an urgent project, which is understanding the issue of non-locality in doubly special relativity. DSR, I think we talked about, is the modification of special relativity to preserve a minimal length. With it, intervals of the Planck length or time don't contract or dilate. This has a consequence which is testable, which is that the speed of light depends on energy." A former postdoc, Sabine Hausenfelder, published a paper arguing that there are non-localities in the theory which are so severe as to rule it out already.
Okay, so that's the point I was trying to make. You see where I'm going with this? We have a discretization of space-time, which doesn't allow for the normal, in quotation marks, sort of rules in general relativity where lengths contract and times dilate below a certain level, like the Planck length or something like that. And she's saying that, okay, so there's the problems emerge to do with non-localities. I think she said that was it. But there's a bigger issue that it's just becomes discontinuous, doesn't it? If you're saying that it's smaller scales, the rules don't apply, then it breaks everything from the smallest scales up to the larger scales, and also causes these problems to do with non-localities. So I'm just curious why, if it's not allowed in this situation, how we can have a disconnect to do with entropy and energy and all of these really important things at a smaller scale, but not at a larger scale. Maybe they're saying, oh, hey, in this particular very, very specific example where everything is, it's an experiment, it's all controlled, and we're using a metamaterial, and we have group waves with, it's like this very special example where this occurs, and it couldn't be something that happens generally, and so we can't use it for like infinite energy or something like that. I don't know. It just sounds, if that's what they're saying, then fair enough. But do you know what I mean?
Yeah, one of the things is that I think it's singularity. It's a question of singularity, right? Yeah. So, in order to get around the singularity, how do you describe the singularity? It's a disconnect, actually. A singularity is a disconnect. So, it means that how the disconnect, like defects can disconnect things, right? If you have a lattice and suppose you are putting yourself in a particle, it's a pure state. The time is different. If you are putting in environment separately, it's different. When you are putting yourself where the particle and environment are together, mixed together, again, that's a mixed state and totally different realm of reality. And the same way, there's a defect. You are in the defect. Like there's a big hole. You are in that sinkhole, right? You see things differently than from the outside you see the sinkhole, but you are in the general environment. But you move away from it, then you are nice environment, right? Nice environment with it. You suddenly keep going, suddenly you hit a pothole or sinkhole. It's a totally different reality you are in. Yeah, it's something like that. If you are driving along and you hit a pothole or a sinkhole or something, it's totally different. You are the whole brain, everything is totally disconnected now from the real
Right.
from the
Yeah.
real
Yeah. No,
world.
I mean, there could be something to it. I'm not entirely denying it. I just thought that it was an interesting thing. So if that's the case, then I mean, I think Lee does say that he goes on to say that he came up with a way to. Oh yeah, I'm really okay. So I think I've been working hard to try and find a way out of our argument. I think I've succeeded. I'm really proud of one of the papers which I've just posted. The idea is that there is a cosmological consequence of quantum gravity, which is a limitation on how far two clocks can be and still be synchronized. Oh, sorry, how far away two clocks can be and still be synchronized. So there could be ways around it, and I suppose those similar ways could be applied then to this other entropy thing as well. Maybe it's just I suppose it's interesting. It is complicated, and yeah, I'm not sure that I'm not interested in it. It's very much related to your work, I think, with the discontinuum, and then you have this other reality that's sort of disconnected. And I think that what you guys are talking about then is far more sort of it's easier for like someone like me to grasp. I like listening to yourself and who is this again? You're Emery, yes. Like that's easier for me to understand. Like when Emery explains that, I can like interpret it in a intuit what he's talking about. I think if we were to read that paper that's related to the group velocity waves and all that, I would say it would be far harder to understand what they're talking about, simply because they probably don't have. They're not willing to be as bold, maybe, as Emery to say, "Look, there's another world down there," And, yeah, and that's what you need. You need someone to step up and say, "Look, we're talking about another universe," and yeah, but because that probably becomes difficult within physics, because how can you prove this kind of wild statement, if you like, and through physics? And I think they would probably maybe have trouble with that. But then wouldn't you just like use what you're saying, like a singularity? You have the language, you have the mathematics to sort of talk about these things. But I guess the problem with singularities is that they are a problem within most models, aren't they? Like the UV catastrophe and all, where you have some sort of exponential explosion. But then that was smoothed out by using the idea of discrete summations or whatever. But the issue there is I always thought that the discrete summation part comes in at a certain limit, get to the Planck length, let's say, and then beyond that you need some sort of discrete integration. But that's not the case. You're actually doing it, for the whole system. So, okay, it is happening on a quantum scale, but there's no reason why you couldn't keep going up in scale.
Extrapolate.
Right. So then the issue then, I think I don't know that for certain, but the thing that I was surprised at is that there wasn't a limit in the quantum scale where you switched into a discrete summation. It was always.
I do show that. I saw that. I show in the most recent paper. I show that how the switching occurs. At what level? Like 10 to the minus 15, 16 to 15 to 16. Meters.
Okay, but why doesn't
I showed in this. If you go back to my presentation,
sure,
you see that. Yeah. You want me to pull up that aspect?
Okay,
So let
here we go.
me pull up that. Um,
Right, so 10 to the minus
Oh,
15, that's around the electron radius, or no,
yeah.
the electron,
It could be
yeah.
the Bohr radius or the classical Bohr radius versus the quantum, you know, electron radius.
So you're saying that
Bohr
above that
radius versus the
radius,
classical.
you're saying that
Bohr
above that
radius versus.
radius, you're saying that above that radius, the equation for Planck, the Planck energy scale or whatever doesn't work?
Well, when you go, it changes, it switches from the,
And have you proved that experimentally, like with?
yeah, not actually mathematically, yeah. I
Well,
don't like,
I mean, surely there's been lots of experiments done into energy, haven't there? So you'd be able to
I'll show this one later about this
you'd be able to
America,
do your
right?
mathematical equations and extrapolate above the Bohr radius, and then show how those compare with actual measurements that have been taken. Until you do that, I don't think you can say for sure that you're correct, can you?
No, this is well known, right? I had to go back and check when the
Oh,
what is the Bohr radius, electron radius, and the classical radius. They 10 to the minus 15 and 10 to the minus 18, I think. That's something
I think it's 10 to
in
the
that
minus
range.
16, isn't it? For the
Yeah.
classical radius of the electron.
And its Bohr radius is slightly smaller. Isn't it?
Maybe. I don't know, actually. What's the Bohr radius?
Bohr radius is we can look at that. Is the very broad, I mean, it's a cloud, right? It's like a cloud. But quantum mechanics says this it's not a clear cut thing, it's a cloud, and they estimate the
But
size of the
was
thing.
I didn't think Bohr was the one who came up with the cloud. I thought he was more prior to that.
And let's look at the electron radius. Maybe in that one will show up.
I mean,
It is
maybe
the classical thing.
wasn't Bohr the one who came up with the classical electron radius, or who was it?
No. It was based on Rutherford, Maxwell, all those people, right?
Yeah, but someone actually came up with the measurement of 10 to the minus 15. Who was that?
Yeah. So it shows here electron is combination of fundamental physical quantity length of scale. So it's based on unit of measurement. So just classical physics, electrostatic self-interaction. It's a very simple definition. Let's see where derivation shows the derivation, right? So derivation classical energy necessary to assemble amount of Q sphere of radius. So it's a simple Q over R. This is a fundamental equation, right? For charge, connection between charge and the voltage or the potential. And from there, they derive Fear assumed to be constant charge density. That's how you get a constant charge density, right? The charge densities come into picture there, and then you have
Okay, but what are we trying to prove here? We're asking what the Bohr radius is. You're saying it's different, or it doesn't really matter. I don't think, Rajan. We've got a number there. But in order for you to prove
minus 15.
you need to extrapolate. You need to extrapolate over the energy. Show that you're now no longer summing, discretely, but rather smoothly. And then you'd have to show how you would go about doing that. I guess I suppose it's just discrete Euler, and then I don't know how you're going to do that. Like,
let me check. Let's quickly check.
Yeah.
Oh, there it comes there. Anyway. All right.
Okay, so it's different. It's minus 11. So it's slightly
Yeah.
bigger or slightly.
Yeah, bigger. Yeah, it will be bigger because you are talking about the cloud, right? Cloud means the Born radius. Let's look at
Oh,
that.
okay. I didn't realize that.
Yeah. See, in the quantum mechanics, it says that doesn't exist as one single particle, but it's like a cloud. It's all botched out cloud. It's a big cloud,
Mm.
and they are trying to estimate the size of the cloud, right? And of course, it'll be larger. It's spread out. So it's defined as H over M naught C alpha, uh, permittivity and all that. So from there, they find out it's 10 to the power minus 11 or yeah,
But there's the Bohr model, isn't it? So it's not a cloud.
yeah.
It's more like a solar system, a planet going around a
No,
sun.
you see the cloud here. And
Uh,
this
but
is the
Bohr
probability
model
of finding.
really is
Oh,
a discrete electron particle going around a
yeah,
proton.
it's a probability function, right? The
Stop.
probability function.
Go back up. Go back up. It says in the Bohr model for atomic structure, electrons orbit a central nucleus. Is that not more like the? Doesn't seem to be talking about a cloud, Rajan, or probabilities.
Let's look at.
In the simplest atom, hydrogen, a single electron orbits the nucleus at its smallest possible orbit with the lowest energy, has an orbital radius almost equal to the. So it's talking about the orbital radius of the electron rather than the classical radius of the electron. Do you get me?
Yeah.
I think. But it is not exactly the Bohr radius due to the reduced mass effect. So that seems to be a different thing. And that's interesting, though, that the Bohr radius then of the orbit is very close to the size of the electron itself. Well, given orders of magnitude, I guess, what is it? It's off by 4 or 5 magnitudes of order, which is kind of big. It would be the difference between a meter and kilometers. Yeah, okay, fair enough. So
large.
I don't want to say, because we're just obviously read a blurb there at the start, so things can get more complicated, but that does appear to be the answer to that question. So I don't think the Bohr radius is what we're talking about. We're talking about where you're closer to 10 to the minus 15. So that's more the classical radius of the electron. So you're saying that above the classical radius of the electron, discrete things no longer matter, but they kind of do.
Yeah.
So there's a fuzzy line somewhere, which can be, because the way we can do weird things with buckyballs, like particles, carbon atoms in the shapes of buckyballs, and we can get quantum effects out of them, even though they're much larger than 10 to the minus 15. So that's okay, I think. Is it? Okay.
Yeah.
So these are the questions we're asking. It doesn't seem like there's a hard limit you're putting a hard limit 10 to the minus 15, but we know that there is no hard limit. So
it's a transition. You see that?
I don't see that. I don't see what that graph means at all. Sorry, Rajan. Doesn't mean anything.
Okay. This is the entropy. How the entropy, if it is less than 10 to the minus 16, right? The entropy is very low, almost zero. When you go to the higher level, this is a quantum level. If you go to sub-quantum level, then the entropy will be zero. Now, above the quantum level, the entropy starts increasing. And then around 10 to the minus 15, it becomes the macroscopic thing. So this entropy-driven time, here, it becomes irreversible. Here, time is reversible. That's what it means.
Oh, okay, I see that. But how are you proving that? Or?
Yeah, all this using discretized.
Talking about entropy is different to talking about the discontinuum, isn't it?
Entropy, I showed the equation.
At the same time.
This is the equation for entropy.
Where's the discrete versus continuous changeover?
that's highly involved. It's in these it is in these papers, and the actual derivation is so involved. I don't want to show it here.
Is it in the
I'm
paper?
just
There's some equations that go into that or something.
yeah, there are a lot of these papers that we go down 6. Self-organized criticality. I mean, there's a lot of things. And a lot.
Well, that's more about
Black
entanglement.
holes and entropy.
So you're saying that the changeover from discrete to continuous is an entanglement thing. That's kind of well known, though. But yeah, I don't know. It's just that is not that's not concrete enough for me to agree with. Do you know? At this point, it's just too fuzzy. There's too many questions involved there. That's not a bad thing, though. I'm not putting down your work or anything. I just think it's obviously a complicated issue, and we can get lost in the weeds. A bit, you can start referencing other people's work and say, well, this is kind of fuzzy cloud related to what I'm talking about. But unless there's, I suppose usually, you'd want some sort of really hardcore mathematics or proof or, show that you're.
These are actually proving that, because you can only prove with what other people have done, and if it is, if it is thing, because I cannot invent Newtonian. Newton did that. I cannot redo Newton's work. It's already there.
All I'm saying is that you would need, well, the thing we're talking about here is can continue, the break between continuous and discrete happening at a small scale. You said you could show that in your paper. Instead, you showed the entropy thing. Now, you didn't show the discrete properties, so that's not there. You say it's highly involved, and it seems to be in references from other papers, but it's not in your paper. So we can't discuss it at the present time.
The cross graining. The cross graining is the main thing.
Cross graining is a discrete thing.
Yeah, the discrete discretization.
When we don't know the actual answer, so we say, "Oh, let's just coarse grain it," which is kind of what we're doing with quantum mechanics.
No. Yeah, we know that discrete action, which means that the action is not continuous. In this case, it's a discrete action.
That's what we're talking about. Why did you interrupt me? I never said anything that discounts that.
Okay.
I mean, a discrete action, you could just say, well, we don't know the continuous function, so we'll just use a discrete Euler, Lagrangian. But that's just
no. The continuous thing is, normally it is what? Integral of Lagrangian over time. That's all action is. What action? What is action? Continuous action. S is integral of L dt. That's all. It's a very simple equation. That's continuous action.
The action is different it's not a Lagrangian.
It's a Lagrangian, but this is a discrete Lagrangian. That's all the difference.
Okay, so why did you interrupt me again? It seems like we're talking about the same thing.
Yeah.
Okay.
Yeah, essentially, yeah.
So the point is that we use the discrete one because we don't know what the continuous function is.
We know continuous function is.
We don't know, well, because actually, not only do we say that we don't know it, we say that it doesn't exist in the quantum scale.
Oh, in the quantum scale, okay. In the quantum scale, it's discrete, yes. That's right.
Okay, so at a certain point, then your discrete action would have to switch over at this 10 to the minus 15 into a continuous one. But see, this goes back to the problem that Sabine Hossenfelder is talking about with the length contraction thing in the general relativity of Lee-Smolin quantum gravity, because at any point where we take like a more continuous one, each of those blocks of continuous, energy or whatever, it can be like discretized again, and then you get back to the thing. So, but to prove it, you would presumably need to get some measurements from a low scale on the order of the Planck equation and all of that, and above, and then show that your equation, which we don't have here, but presumably you have one, yours and Emery's, that it matches the experimental results. And in that case, I think you would have a solid theory that I would back, But until then, I just don't see it,
Let me show you one of our recent papers, the discontinuum. Okay, so this is our website, right? Where Emery has put this, not me.
No,
Emery has put this,
Einstein working with
and
you.
he has these people who are all well known.
They're honorary members of what?
These are all De Broglie and all those people.
Okay, they're just people that you admire or whatever.
Yeah, I mean, especially Emery. I agree with, if it is reasonable for me, I agree with him. Not everything I agree with him, not necessarily, but that's how we come up with this paper. Wherever I agree, I come up with the paper. So let's look at the recent paper. The papers are Zalkin paradigm shift. Yeah. Okay, in this paper, right, we are just putting out now this paper. It's the most recent one. Let me go down where I did the math for him. So this is the description. He has given this schematics, how the simple harmonic oscillator actually you have to interpret correctly because it stops here and things before it changes. So that was not taken into account. So that appears in the sinusoidal wave, which is a continuum, right? It's a continuum. Then we have the discontinuum, which I graphed. I did the mathematical modeling, and I showed that the discontinuum you can have a break here. Okay,
right?
So it's not
you
continuous.
can't use
It's a
the
break
equation
here.
for a simple harmonic oscillator at the quantum scale. It doesn't work.
Yeah.
But why are you saying yeah?
Huh?
I mean, you
What do
just
you mean?
can't use a simple harmonic oscillator at the quantum scale. It's just different. It doesn't happen.
No, I'm saying this is a simple harmonic motion.
Yeah, but you're trying to say that this is at the quantum scale, but that's not how that works.
Well, it's below our macroscopic level, not necessarily a quantum scale. So when you talk about, we are not really.
I don't know. It's we're getting fuzzy. You're either trying to do the quantum thing or you're not. You seem to be hedging your bets here. It's below the scale, but it's not quantum. But the thing is supposed to show quantum discreteness. So it's contradictory.
No, there's a transition point. There's definitely a transition point between the quantum level.
There's no like hard transition point because we can have quantum effects above that point.
I mean, it flows into, like, if you look at the quantum tunneling, for example, right? It happens only below certain scale, but it becomes fuzzy when you approach the macroscopic. So actually it doesn't tunnel like the normal level. If you throw a ball, right, it doesn't tunnel into the other side, so the ball stops it. But the quantum level, the electron can be considered as a small ball.
Yeah, but if you look at like Schrodinger's cat experiment, that's an example of how a quantum effect could bleed into the macro scale and produce a superposition of a cat that's both alive and dead at the same time. So there, according to conventional physics, there is no division. Do you get me?
What do you mean by that?
There is no hard division between the quantum scale and the macro scale because we can set up experiments in such ways that they blur the line to not just up to like 10 to the minus 15 or 10 to the minus 18 or whatever, or up to buckyball size, but actually all the way up to the size of a cat, and possibly even higher if you're using. Actually, recently I saw an interesting video about what was it? It was to do with gravitational lensing around. So you have a galaxy in the far distance, or this way, and then another one in front, and like the light comes through, but it can split into these 4 images. And so they were discussing that in terms of the double slit experiment. So if you, instead of using 2 slits, if you use like a needle, like the way or like a human hair or something, and then you have a laser going through, so it can go through on either side and then interfere on the other side. So they were suggesting, if you have like the photon can go through both sides at the same time, which would imply that when you have this these 4 images on the around the galaxy, that they that a photon could then leave the star and go around both sides of the galaxy at the same time. So it's like a double slit experiment, but on a galactic scale. It's pretty interesting. It's kind of an interesting bridge between maybe general relativity.
Like interference measurement, right? The normal interference measurement, where they split the light.
Yeah, exactly. But it was more. It was kind of going back to the idea of
spectrometer and all.
Wave function, probabilistic wave function, all being interfering to create like the actual path of a particle, and that's kind of your macro scale interference with the entanglement and all of that as well. So it's pretty interesting. Okay, Rajan, I think we've gone on for about 2 hours, and I'm
yeah.
But that was a good conversation.
Thank you.
I might see you next week. We should talk about what we're going to do.
No, 2 weeks time. Yeah, in 2 weeks time we usually are doing every other week, right? So the next one will be March 7th, I think. Isn't it March 7th?
Yeah.
This year is only 28 days, February. So it'll be March 7th. So March 7th, you can come up with something. Right now you have to come up with something. You have to put the link.
We could do another sort of conversation on this subject matter, maybe. We'll have to see. Or unless you have some other research you want to share.
I will have one more I am trying to finish. Hopefully I will finish my paper and send it. But I don't know, I can discuss some aspects of it. Mainly it is hadron lattice, continuation of that. So early universe, then you have this quantum lattice, then you have the hadron lattice, how the hadrons form a lattice and creates the gravitational waves, So that's the next one.
Okay.
And after that, what you talked about, chirality and parity.
Okay, yeah, that's a small issue, but yeah, that sounds good. All right.